Welcome to the second video in our Class 17 series of lecture videos. We started off with the first one describing a little bit of naming of alcohols and then some of their physical properties. Let's resume with our study of alcohols by investigating their pKa values. So pKa refers to how acidic the most acidic proton is on that molecule. So we know the pK of water is 15.7. I know we lied to you. We told you it was 14 in general chemistry, but we have to take certain things like the concentration of water in water into account. And then we, organic chemists, come up with a number closer to 16. So 15.7 for the purposes of our class. How does methanol compare to that? Well, its most acidic proton is, of course, the proton attached to the oxygen. Its pK is 15.5, so almost identical. Higher pKa means less acidic. As we go to ethanol, we see the pKa is rising slightly, 15.9. Isopropyl alcohol, we're up to 17.1. And then tert-butyl alcohol, we've hit 18. That's almost a couple orders of magnitude less acidic than water or methanol. So what's going on? Why does pKa increase as we add more carbons to our alcohol chain? Well, this could potentially do with poor solvation of the conjugate base. So when we lose a proton, something that stabilizes the conjugate base, which would be an alkoxide, is the ability of water or other alcohols to coordinate around that oxygen. The more and more carbons that you have and the bulkier the group, the more difficult it's going to be to solvate or create these hydrogen-oxygen interactions between other solvent molecules and the conjugate base of our alkoxide. So poor solvation of the conjugate base, also inductive donation of the alkyl groups. So carbon has more electron density, and more carbons bonded to the carbon that's bonded to the oxygen are pushing even more electron density into the carbon, which then pushes it through its sigma bond into the oxygen, making it more difficult for the oxygen to sustain that negative formal charge. Here we go. Here's a neat trick. Here we've got methanol and we have sodium amide. I have a big bottle of this in my lab. Very flammable, especially when you put it in water, can be explosive. We're going to create sodium methoxide and ammonia. That's going to bubble away pretty quick. pKa of ammonia is 35. We know the pKa of methanol is 15.5. The KEQ for this acid-base reaction, you can pretty much summarize that as 10 to the pKa of the conjugate acid minus the pKa of the acid, if you're looking at this reaction going from left to right. So that would be, in this case, 10 to the 35 minus 15.5, or about 10 to the 20. We put 10 to the 19.5 just to be exact in our math. So this number is greater than 1, much, much greater than 1, which means we really favor the products, right? And so at the end of our reaction, we're going to have all sodium methoxide and ammonia, and none of the sodium amide and methanol left over. How can you lower the pK of ethanol? Well, I guess you can change your molecule, your ethanol. You can do this through something called inductive withdrawal. So here we have ethanol. Its pK is 15.9, as we observed. What if we change all the hydrogens on the methyl termini of ethanol to fluorines? Well, those pull electron density out of the carbon, which then pulls it out of the carbon that's bonded to the oxygen. And if that's pulling electron density out of the oxygen, well, the conjugate base of this molecule can better stabilize the negative charge on oxygen. And hence its pKa is lower, 12.4, a little lower by a little more than 3 orders of magnitude, so more acidic than ethanol. Of course, if you put those fluorines further away from the hydroxyl group, it's less of an effect. We only go down to 14.6 for this molecule. Another way, you can stabilize a conjugate base by resonance too. What do I mean by that? So cyclohexanol has a higher pK than phenol by 7 orders of magnitude. So what do I mean by the conjugate base is stabilized by resonance? Well, the conjugate base has to do with the molecule you get after you lose the most acidic hydrogen, which is, of course, is the hydrogen bonded to the oxygen. So for cyclohexanol, the conjugate base that you get is this cyclohexyl alkoxide. For phenol, your conjugate base is phenoxide, and we lost that hydrogen atom. For our conjugate base of cyclohexanol, that negative formal charge is stuck on this oxygen. I can't push it down to this carbon because that carbon it has 3 other bonds, and so we can't move anything around. We'd have to break one of these bonds. You'd either break the ring open or you'd send a hydride atom packing into the universe. It'd be very unusual to try to push this electron pair onto this carbon. However, for the phenoxide, because we have a double bond here, we can push a lone pair down and then move the 2 electrons in that double bond over to this carbon. And so we can generate a resonance form. And here we go. We can generate another resonance form, so put that formal minus charge on the carbon opposite, the carbon bonded to the oxygen, which now has a double bond. And then we can keep going to put that formal minus charge over here on this carbon. And this kind of actually gives us an idea about where phenol might serve as a nucleophile in terms of carbons relative to where that OH group is. We'll delve a little more deeply into that in the second semester. So, alkoxides are the conjugate bases of alcohols, as we discussed. If you put, an equal amount of sodium hydroxide in methanol, of course, water having about the same pK as methanol, if you do your little trick to calculate the KEQ, you're going to get about 1 if you start out with, equal concentrations of hydroxide and methanol. However, you can use Le Chatelier's principle to surmise that if you put 1 small pellet of sodium hydroxide in methanol, that huge ocean of methanol is going to help push this equilibria over to the right. So you will have mostly methoxide and a little bit of water in your solution if you just put a small pellet of sodium hydroxide in an ocean of methanol. Sodium hydride is a wonderful reagent to use to deprotonate alcohols. We always use this as a base. It's always a hydride, so hydrogen has a greater electronegativity than sodium, and it owns the electrons. This hydrogen, we're used to seeing hydrogen as electrophilic, so oxygen's more electronegative than hydrogen. So it's this is the oppositely tuned hydrogen. So we call this a hydride, and this is more like a proton. So of course they're going to get together, they'll create hydrogen gas, which will bubble off. pK of that is about 38, and we get sodium methoxide. This is, a great acid-base reaction. KEQ is 10 to the 38 minus 15.5. And, since the hydrogen leaves, Le Chatelier is also driving this reaction. It's important to note that proton transfer is faster than SN1, SN2, or E1 and E2. So if we put in sodium hydride with this molecule that has a hydroxyl group and a primary carbon electrophile on it, we'll deprotonate this. It'll make a great nucleophile, which will actually do an intramolecular SN2 and give us this ether, cyclic ether. So that pretty much does it for our second lecture video. I'll see you in the third one.